Yeah, so I've started the recording now. So, did you attend? Have you attended my last class? Last week, did you attend the class? If not, also there's no problem. Maybe I'll. So, in last class, I taught how to make shear force and bending moment diagram. So, I've covered few points. So, in this class, I would like to continue that. Plus, I would like to tell that how to make the loading diagram from the shear force diagram. Okay. So, firstly, I'll quickly revise the things which I've told in the last class. Okay. So, you can easily make the shear force and bending moment diagram using, if you keep in mind some important points. Okay. So, I hope these points you have already covered in your SOM class, but I'll quickly revise those points. The first point is the slope of the shear force diagram is equal to the intensity of the distributed load. Okay, so these few points will be helpful in drawing the shear force and bending moment diagram very quickly. Okay, because in GATE you don't have that much time to calculate each and everything. So by keeping in mind some of these points, you can easily make the shear force and bending moment diagrams. Okay, so the first point is the slope of the shear force diagram is equal to the intensity of the distributed loading. The second point is the slope of the bending moment diagram is equal to the shear force at that section. These are the first 2 points. The third and a very important point is the change in the shear force is equal to the area of the area under the distributed loading between those 2 points. Okay, for now, just keep in mind these points and then I'll tell you how to implement these. So the change in the shear force equal to the area under the distributed loading between those two sections. So we can also write it as V2 minus V1, that is the change in the shear force, equal to the area under the distributed loading. Okay, so here we do not have to do any integration. It's just symbolic thing. Okay. The fourth point is the change in the bending moment diagram is equal to area under the shear force diagram between those two sections. That is M2 minus M1, which is the change in the bending moment, is equal to area under the shear force diagram. Okay. Some other additional points: downward point load causes the shear force diagram to drop by that much amount. That is, if the intensity of the point load is F, then the shear force diagram will drop by F amount at that particular section. Upward point load F causes the shear force to jump by F amount. Okay. So the upward point load F causes the shear force diagram to jump by F amount at that particular section. Similarly, clockwise bend. So these 2 points are for the shear force diagrams. So whenever we encounter a downward point load F, then in the shear force diagram will drop by F amount at that particular section. The last 2 points are for the bending moment diagram. The clockwise bending moment diagram causes the clockwise moment causes the bending moment diagram to jump by m amount, and the anti-clockwise bending moment diagram anti-clockwise bending moment drops the bending moment diagram by m amount at that particular sections. So using all these points, in total there are 8 points, 4 formulas. So please note down these formulas. Okay, and 4 points. Okay, so these 8 points you should remember while drawing the shear force diagram and bending moment diagram from the loading diagram. Also, they will be helpful in drawing the loading diagram from the shear force diagram, because these type of questions are also asked in GATE and engineering services examination. Okay, then we need to see some different slope types. Okay, this is a zero slope. Zero slope means no slope at all. This is a zero slope line. This is a constant positive slope line. This is a constant positive slope line. Okay. No, please note down these things also. So this is a zero slope when there is no slope. it is a constant positive slope. Slope is constant and it is in upward direction, so it is a constant positive slope. Similarly, it is a constant negative slope. Okay, this is called a positive decreasing slope, because here it is positive. Why? Because it is going in upward direction. Why it is decreasing? Because here, if we draw a tangent here, at this point the slope is theta, but here the slope has decreased. Okay, so theta 1 is more than theta 2, so slope is constantly decreasing, but it is a positive slope. Okay, so it's a positive decreasing slope. Then negative increasing slope, it is going as downwards, so it's a negative decreasing slope, and slope is constantly decreasing. And finally it is a negative decreasing slope. Here it is a negative decreasing slope. So these slope types you should note down, because they will also be helpful in drawing the SFD and BMD. They are very important. They will help you in finding out the SFD and BMD of a loading diagram very, very quickly. Just by seeing the options, you can tick mark the correct option even before doing any calculation. So these slope types are very, very important. So what all the things you should remember for drawing the SFD and BMD? Firstly, the 8 points which I have told you, 4 formulas and 4 points. Another thing is slope type. So these are the different slope types you should remember. So now you are all set for drawing the shear force and bending moment diagram very, very quickly. Okay, so these were the few questions which I have discussed last week. If you want, you can see the recording of the previous week and see how these problems are solved. For this class, I'll solve one problem, that is drawing the SFD and BMD diagram using the points which I have told you just now. So how to solve this problem? First of all, for drawing the SFD and BMD, you should know the reaction. Okay. So how to calculate the reaction in this case? So you can do it by the conventional method you must be doing in your classroom. Also, you can do it in some other method which I am telling you. Okay, so for calculating the reactions, what you can do is, if there is an uniformly distributed load, you can draw it as a point load just for calculating the reactions. Okay, so I am making it a point load, and the intensity of this point load will be 2 into length. So because it is W, that is unit load 2 kilonewton per meter, so total weight will be 2 into the length in which it is distributed. So it is distributed in 5 meter length. So the total intensity will be 5 into 2, that is 10. So this uniformly distributed load can be replaced with a point load like this. Okay, so and distance will be half of the length. Okay, so this distance will be, the entire length was 5 meter, so this distance will be 2.5 meter. So the remaining length now is 7.5 meter. So this thing we can do only for calculating the reactions. Okay, so whenever there is a uniformly distributed load, you can convert it into a point load in this way. The intensity of the point load will be W times the length, and it will be placed at the mid length. Okay, so if it was 5 meter total, so I'm placing it at 2.5 meter here. Okay, I hope it is clear. If there are any doubts, you can ask me by unmuting yourself. Okay, so now how to calculate the reaction? So the reaction for this point load will be, if we are calculating the reaction, let's say it is A and it is B. If we are calculating the reaction at A, it will be point load multiplied by the other half distance, the other distance, okay, which is 7.5 meter, divided by the total length of the beam, which is 10 meter. Okay. Similarly, if we are calculating the reaction at RB, okay, we can calculate it by point load multiplied by the, for this support B, for this support B, the distance we will take is the other distance, which is 2.5 meter in this case. So 2.5 meter divided by 10. So this is, in this simple way we can calculate the reactions. We do not have to do like moment at this point equal to 0. In that way also we can calculate the reaction, but it is a quick way. Okay, so I hope it is clear. So this reaction at A will be 7.5 kilonewton and this reaction will be 2.5 kilonewton. Is there any problem? If there is any problem, you can stop me anytime and I'll explain it again. Okay. So this is the method in which you can calculate the reaction whenever there is a point load. Okay. So first of all, I converted this uniformly distributed load into a point load, and then I have calculated the reaction, which is 7.5 meter for this support, A support, let's say, and for B support it is 2.5 meter. So in this way you can quickly calculate the support reactions. So now we can remove this part because we have already calculated the reactions. Now the sign convention which I'll be following, and I have discussed that in the last class, will be this. So this is the sign convention and I'll follow for this, for drawing the SFD and BMD here. Okay, now I have calculated the reaction. Now I'll start making the shear force and bending moment diagram using the points which I have discussed before. Okay, so now to make the shear force diagram first. So I have discussed this formula, that is V2 minus V1, that is a change in the shear force, is equal to the area under the distributed loading. Okay, so now at this point, first of all, there is an upward load. I'll start by making the SFD from this point. Okay, so let's say at this point there is an upward load of 7.5 kilonewton. So using our sign convention, on the left side of the section, if the load is upward, it is positive. So it's the left side of the section and load is positive. So I'll make it as 7.5 kilonewton. Okay, so at this point I know the shear force at this point. Now the section is this. So at this section, let us call it as section C. What will be the shear force? So I'll use this formula, V2 minus V1 equal to integral over Wx dx. V2, that is, let's call it as section 1, let's call it as section 2. Okay, so V2, that is the shear force at section 2, we do not know, right? So V2 we do not know, V1 we know as 7.5, and what is the area under the distributed loading is minus 10 kilonewton. Why? 5 into 2, and downward loading is negative. So 5 into minus 2 is minus 10 kilonewton meter. So V2 will be minus 10 plus 7.5 kilonewton. So V2 will be minus 2.5 kilonewton. So now we have calculated the shear force at section 2, which is minus 2.5 kilonewton. Okay, so there is another thing, that W is equal to W equal to this formula, this thing we'll use. So till now I've used this, that V2 minus V1 equal to W dx. There's another thing, that dV by dx, that is the slope of the shear force diagram, will be equal to the intensity of the distributed loading. So now to calculate the slope of the shear force diagram, we will use this part. Okay. Yeah. So now we know that at section A the shear force is 7.5. We know at section C the shear force is minus 2.5. Now, but what is the slope? How to join these 2 points? Should I join it using this thing, using this slope? Should I join using this slope, or should I join using this slope? We do not know at this point. So how to join these 2 points? For that I'll use W equal to dV by dx. That is, slope of the shear force diagram is equal to the intensity of the distributed loading. So as I've told you earlier, that downward load I'll consider as negative. So what is the intensity of the distributed load? So area of the distributed load is negative because it is a downward load for the section AC I'm talking about. For the section AC, the distributed load is downward, so I'll consider it as negative and constant. It is not either, it's not increasing or decreasing, right? This is increasing distributed load. This is decreasing distributed load, and this is constant distributed load, right? So for section AC, the intensity of distributed loading is negative. Why negative? Because it is in downward direction and constant, negative and constant. Since the intensity of the distributed loading for section AC is negative and constant, therefore the slope of the shear force will be negative and constant. So I'll repeat it again. Since the intensity of distributed loading for section AC is negative and constant, therefore slope of the shear force diagram will also be negative and constant. Let's check what is negative and constant slope. So from the slope we have discussed here, constant negative slope is this. This type of slope is constant negative slope. Therefore, we will join section A and C using this type of slope. So now I'm joining A and C with constant negative slope. Is there any problem, or should I continue, or do you want me to explain it again? Is it okay? ठीक है. So I'll continue. Now we know what is the shear force at point C. Now we have to find out the shear force at section B to continue the shear force diagram. So at C we know it's minus 2.5. Now we'll consider section CB. In section CB there is no load, right? No, neither any point load nor distributed load, nothing. So at point in section CB it will be constant. The shear force diagram will be constant. Now, when we reach section B, at section B, we can see that there is an upward load, upward point load, which is 2.5. So, upward point load. So, whenever there is an upward point load, shear force diagram will jump by 2.5. So, it is jumping by 2.5. So, here it was minus 2.5. So, it has jumped by 2.5. So, it will become 0 at 0 here. Okay. So, this is our complete shear force diagram. Okay, so using these few formulas, you can quickly make the shear force diagram. Moreover, if in GATE this question is given to you and different options of shear force diagram is given to you. For example, this is one of the option. The other option may be anything. So you using this slope concept, without calculating any reactions, you can just see that at section AC the slope is the intensity of the distributed loading is negative and constant. Therefore the slope of the shear force diagram should be negative and constant. So this is a negative and constant slope, so this could be an option. This is not a negative and constant slope. It is a negative slope, but it is not constant. Therefore this cannot be the answer. So you can rule out the options without even solving the reactions. Okay, so this technique will be helpful whenever the options of SFD are given. Okay, so without calculating any reactions, you can just tick mark the answer just by seeing the slope. Okay, so that is why this technique is very, very powerful. Okay, now you have calculated the shear force diagram. Now we'll see how to make the bending moment diagram using this technique. So shear force diagram is done. I hope there is no problem. So this is a positive part and this is the negative part of shear force diagram. Now we'll see how to make the bending moment diagram. So this is the shear force diagram. After making the shear force diagram, we'll make the bending moment diagram. So for bending moment diagram, we will use this thing M2 minus M1 is equal to integral over v dx. That is the area of the shear force diagram for that particular section. So let us call it as section 1 and this as section 2. Also, if there is a this there's a section, there's a like as shear force is becoming 0 at any section, so we have to make this as section as well. So here we will have another section. So we'll call this as section 1 and this is section 2. Let's start making the bending moment diagram. So at, let's call it section A, this is section B, this C, and this is D maybe. This will be D section. Now at section 1, at section A, we know that bending moment is 0. Why? Because section A is there is a hinge support. So at A, the bending moment will be 0. At B, the bending moment will also be 0 because B is also a roller support. So at B, the bending moment will be 0. So at 2 points, we already know the bending moment. Okay. Now we will see for section 1 to how to make the bending moment diagram. So we will use this formula m2 minus m1 equal to integral over v dx m2. That is the bending moment at section 2. We do not know right now. The bending moment at section 1 we know, which is 0. Okay, that is which is, and it is equal to the area of the shear force diagram. Now for calculating the area of the shear force diagram, we should know what is this length, right? Because this is a triangle, so area will calculate it as half base into height. So base is x and height is 7.5, but we do not know what is this x. So this x we can calculate using the shear force, using the geometry. Okay, similarity of triangles you must have heard. So how to calculate this length x? So this length x we can calculate simply. So let us call it as x. So if it is x, what will be this length? This will be 5 minus x, right? Because total length is x. So this part is x, the other part will be 5 minus x. And how to calculate the value of x? The x will be 7.5, that is this length, divided by x equal to, that is very simple. I hope you must have read it in school also. So 7.5 divided by this length equal to 2.5 divided by 5 minus x. 5 minus x. So from this we can easily calculate the value of x equal to x, and we will have the value of x as 3.75 meter. So x we have calculated as 3.75 meter. Now we can replace x here, 3.75. If it is 3.75, this length will be 1.25. Right. So in this way we can calculate the value of x. Now we know x, so we can calculate m2. M2 will be equal to half 7.5 into 3.75. Right. So m2 will be 14.0625 kilonewton meter. So m2 we have calculated using this formula, m2 minus m1 equal to area of shear force diagram in that particular section. So area of shear force diagram, from this we have calculated the value of m2 and it is coming out to be 14.0625. So let us 14.0625. Now I have marked this point 14.0625. But what will be the slope of this bending moment diagram in section 1 2? For calculating the slope, I'll be again using V equal to dm by dx, this formula. Okay, that is the area of shear force diagram will be the slope of bending moment diagram. At that section will be the area of shear force diagram. Okay, now how the area of shear force, how the shear force is varying for section 1 2? The shear force is varying, it the shear force is positive but it is decreasing, right? I hope you agree. For section 1 2 the shear force is positive, right? For section 1 2 shear force is positive but it is decreasing. Okay, So it will, this similarly the slope will be same. So slope will also be positive, but it should be decreasing. Okay, because the shear force is positive and decreasing, therefore the slope of the bending moment diagram should also be positive but decreasing. So what is positive and decreasing slope? Positive and decreasing slope looks like this. This is the positive but decreasing slope. So we will join section 1 and 2 in the BMD as this, because it is a positive and decreasing slope. Now we will calculate the value of bending moment for section C. Okay, so now let us call this as section 1 and this as section 2. We will again use the same formula, m2 minus m1 equal to integral over v dx. m2 we do not know for now, m1 we know, which is 14.0625, right? That should be equal to area of shear force diagram between section 1 2. So area of shear force diagram between section 1 2 is this area, right? This area. This area is as a triangle. So half, why it is negative? Because area is negative here. Half base is 1.25, height is 2.5, right? So m2 will be equal to so m2 will be equal to 12.5 kilonewton meter. So m2 here is 12.5 kilonewton meter. So I've marked it here as 12.5 kilonewton meter. But what will be the slope? Slope we will calculate using this formula. So how the shear force is varying? Shear force is negative and increasing, right? It is negative. You can see from the diagram for section 1 2 the shear force is negative, but it is increasing also, right? This is negative but increasing for this particular section. So similarly the slope of the bending moment diagram for section 1 2 will be negative and increasing. So what is negative and increasing slope? We'll see from here. Negative and increasing slope looks like this. So see how this slope is helping us in drawing the SFD and BMD. So negative and increasing slope looks like this. Therefore, we will join section D, section 1, 2 by negative and increasing slope, which is something like this. Okay, now we have reached at section C and we will move towards section CB now and see how the bending moment diagram is varying. So at section C, we know the value of bending moment diagram. At section B, we'll also know the bending moment diagram is 0. Okay. Therefore, we will see now what is the slope of the bending moment diagram. We do not know how to join these 2 points, right? So we will see how to join now. So for section CB, we know that shear force diagram is negative. For section CB, the shear force diagram is negative but constant. Okay, it is neither increasing nor decreasing. For section CB, the shear force diagram is negative and constant. Therefore, the slope of the bending moment diagram for section CB will be negative and constant. And how does the slope negative and constant looks like? It looks like this, right? Negative but constant. So we will join section CB with this particular slope, that is negative and constant. So this is the slope of the bending moment diagram. Okay, so this is how the bending moment diagram looks like for this particular beam. So you can see how easy it is to make the shear force and bending moment diagram using this particular technique. So you can quickly make the SFD and BMD diagram, okay, using this particular technique. So now we are done with making the SFD and BMD. Now one more question we can also try. Yeah, this is, I guess it was a gate question. I'm not very sure, but in this question, we are given a cantilever beam in which loading is there. There's a point load. Let's call it as A, B, and C. At point B, there is a point load, and at point C, there is a moment. So, four options are given to us, and they are asking what should be the shear force diagram for this particular loading diagram. So, for let's calculate the reactions first in this case. So the reaction will be 2 kilonewton because there's a point load 2 kilonewton. So reaction will be 2 kilonewton. There will also be a moment here, and the value of this moment will be 4. So moment at A will be 2 multiplied by 1, force multiplied by distance, plus there's another moment 4. So moment at A will be 6 kilonewton meter. So we have drawn a moment also, which is 6 kilonewton meter. Let's now quickly draw the SFD for this particular case. So this is the sign convention I'm going to follow. Yeah, for this, for drawing the shear force diagram. Now I'll start by this section, left section. So at section 2, sorry, at section A, there is an upward point load. There's an upward point load of magnitude 2 kilonewton. So from the sign convention, from the at the left side of the section, if there's an upward load, it will be positive. So we have drawn a positive shear force diagram. So it is 2. In section AB there is no loading, right? In section AB there is no loading, so shear force diagram will be constant like this. It will be 2 here. At point B there is a downward load of 2 kilonewton. So whenever there is a downward positive load, there's a downward loading, then the shear force diagram drops by that particular amount. So here it was 2 kilonewton, but now we have encountered a point load, downward point load. So shear force diagram will drop by 2 kilonewton. So it will drop by 2 kilonewton and will become 0. Right? Now we'll see section BC. At section BC, there is no loading. Okay, you should keep that in mind. I've already discussed this in the last lecture, that the moment does not cause any effect on the shear force diagram. So at section BC, there is no point load or distributed load. Therefore, and the moment does not cause any change in the shear force diagram. Therefore, there will be nothing here. So it will be 0. It will remain 0. So what is the option that is matching with our answer? That is option number A. So this is the correct answer for drawing the SFT. Now we will see, I hope it is clear till now. Now we will see how to make the loading diagram from the shear force diagram. Till now I was discussing how to make the SFD and BMD from the loading diagram, but now we will see, because you can also get the reverse problem. Now we can see how to make the loading diagram from the shear force diagram. Okay, so for making the loading diagram from the shear force diagram, we will consider this, we'll see this problem. So the sign convention will remain same. Now we'll start with this section. Let's call it as A, B, C, D. We'll start with section A. At section A, we have encountered an positive shear force of 14 kilonewton. So positive shear force will occur when there's an upward point load at that particular section, right? So here there will be an upward point load of magnitude 14 kilonewton. So it will be 14 kilonewton upward point load. Now, for section A, B, the SFD is constant, right? The shear force is constant. Force is constant whenever there is no loading. So there would be no loading at section A, B. At section B, the at section B, we have encountered that the shear force diagram have suddenly dropped, right? And suddenly dropped by how much amount? Earlier it was 14. Earlier at section B it was 14, but it has dropped to -4. From 14 it has dropped to -4. So by how much amount it has dropped? 14 minus -4. So it has dropped by 18 kilonewton. So at section B, so from section A to B, there was the slope, the shear force was constant, okay. But at section B, we have encountered that the shear force diagram has dropped by 18 kilonewton. So when we encounter a drop in shear force diagram, it means that there is a negative point load, that is a downward point load at that particular section. So we have discussed that point, that if there is a there's a downward load, that downward point load at particular section, then the shear force diagram drops by that particular amount. So here we encountered that at section B the shear force diagram drops by 18 kilonewton. Therefore there must be a downward point load at section B. So we'll draw a downward point load at section B, and it is 18 kilonewton. I hope it is clear. Another thing we notice that from section BC, the shear force diagram is negative. The shear force diagram in section BC is negative, but it is increasing, right? Negative and increasing. Okay, so we will use this formula, W is equals to dV by dx. So for drawing the loading diagram from the shear force diagram, we will see how the slope, so the intensity of the loading diagram equal to the slope of the shear force diagram. So in order to find out what is the intensity of the loading for section BC, we will see what is the slope of the shear force diagram for section BC. So what is this slope? So slope means this theta. So what is the value of this theta? The value of this theta is equal to this multiplied by the length. This part, let's call it, so this part divided by the entire length up till this. The slope we will calculate it as, this length is 16 minus 4 divided by this length is 8 meter. 8 meter. The slope will be, this is how we will calculate the slope. The slope of the shear force diagram for section BC will be 12 by 8. So slope will be, for section BC will be 1.5 kilonewton. Sorry, just not in kilometer. So slope is 1.5. Okay. So using this formula, the intensity of loading is equal to the slope of the shear force diagram. So whenever we need to calculate the loading diagram from the shear force diagram, we need to calculate the slope. Okay, so we have calculated the slope of the shear force diagram for this particular section BC, and slope comes out to be 1.5 kilonewton, 1.5. Therefore, the intensity of loading will be 1.5 kilonewton per meter for this particular section. So there will be a uniformly distributed load of intensity 1.5 kilonewton per meter. Okay, whenever there is a point load, there will be a sudden drop. So here we can see a sudden drop. So we will know that there is a point load. Whenever there is a constant increasing or decreasing this kind of slope, then we will know that there will be a uniformly distributed load at that particular section. The intensity of that uniformly distributed load we can easily calculate using the slope of the shear force diagram. Okay, if it is too much for now, just listen to it very carefully, and you can practice this thing again, and I'll share the recording also. So please listen to this thing again, and you'll easily understand it. Okay, so now we have calculated the loading diagram till point C. So now at point C we can see that at point C there's a sudden jump. There's a sudden jump in the shear force diagram. Can you tell me how much, by how much amount there's a jump here? So it is going from minus 16. It was here minus 16 kilonewton. Okay, and it has jumped up to 9 kilonewton. It was minus 16 earlier, and it has become plus 9. Very good. So there's a jump of 25 kilonewton. So jump means when we encounter a jump we encounter when there is an upward point load. So here we will make an upward point load of 25 kilonewton. Now up till point C we are done. From section in section C D, we can see that the shear force is this is having a negative slope here. And what is the amount of slope? Because the amount of slope is equal to the intensity of the distributed loading. So what is the slope I am getting here? Can you calculate the slope here for section CD? This slope, this slope is this length divided by this CD length. What would be the slope for section CD? The slope for section CD will be 9 minus 3, which is this length, divided by this 4 meter. Slope will be 6 by 4. So slope we have calculated as 1.5 kilonewton, sorry, 1.5 again. Okay, so slope is 1.5 here. So since the slope of the shear force diagram for section CD is 1.5, this means that there is an intensity, the intensity of the distributed loading for section CD is 1.5 kilonewton per meter. So here also it is 1.5 kilonewton per meter. Now, at section D, we have encountered a sudden drop in the, this is section D, right? At section D, we have encountered a sudden drop in the shear force diagram, and the drop amount is 3 kilonewtons. So there must be a, when we encounter a drop means downward point load. At when there is a downward point load, there is a drop in the shear force diagram. So here there should be a downward point load, and the amount of that load will be 3 kilonewton. So this is how we will make the loading diagram from the S shear force diagram. Okay, so I hope this thing is clear to you. You can practice a lot of questions, and after that, this technique will be clear to you. This technique is more powerful than the conventional technique because in gate you have options, so you can rule out those options by seeing the slope of the shear force and bending moment diagrams. Okay, so this technique will be very helpful in that case. Now this SFD and BMD part is complete. I'll discuss another very important thing, that is degree of static indeterminacy of a structure, especially for a rigid frame here. Okay, so there's a gate question number 32 of gate 2008. In this case, we need to calculate the degree of static indeterminacy of the rigid frame having two internal hinges as shown in the figure. Okay, so before discussing this problem, I would like to discuss how to calculate the shear force and how to calculate the static indeterminacy in case of frames. Okay, so there's a technique in which we have to make the open tree like structure. So this is a technique to calculate the degree of static indeterminacy for frames. Okay, how we will do it, we'll see. Okay, so we will have to cut the structure in such a way that each individual part looks like a tree. Okay, so what should be the properties of that tree? So the tree should have only one root. That is, it should have only one support. Okay. Okay. The tree cannot have a closed loop branch. So this, I'm sorry, this is wrong and this is right. Okay. So the tree cannot have a closed root branch. So this structure does not qualify for a tree because it has a closed loop branch. This structure qualifies for a tree because it has one root. So the property of the tree should be, it should have one root, it should have only one root, and the tree cannot have a closed loop branch. So these are the branches of the tree and it is not looping like this. So it is okay. So this thing qualifies as a tree, but it is not a proper tree. So we will see how this thing will be useful to us. So in this case, we are saying that in order to calculate the static indeterminacy of a structure, we need to cut the structure in such a way that it will form open tree like structure. Okay, so whenever suppose there is a structure, there is a frame. Okay, so in order to calculate the static indeterminacy, we will cut this. So when we will cut this thing from here, what will be the structure we are getting? We'll get a structure like this, plus we will get a structure like this. So this cut is proper. Okay, so this cut is proper. Why? Because we are making two open tree like structure. This why this thing qualifies as a tree, because it has one root and it has no looped branches. So branches are open. So it has one root and it is has no looped branches. So in this way we have to make the cut. These points we need to keep in mind for making the cut. Okay, that is only so these 2 points are only important for making the cut. So in this way we can make the cut. So this is the right technique to make the cut, in which we have these two structures. Also we can make a cut like this. Suppose this was our frame, so we can make a cut like this also, because in this case we will have one structure like this and another structure like this, right? So this is also a correct way of cutting. So we can make a cut like this. Okay, so this thing is clear now. So now we'll see how to use the thing, this open tree like structure technique. So in this technique we have to make a cut in the structure such that it will make open tree like structure. Secondly, we will calculate the value of degree of static indeterminacy using the formula now, that 3c minus r dash, where c is the number of cuts, where c is number of cuts to make it an open tree like structure, and r dash is number of restraints to make the joint rigid. We'll see how to use the formula, but you should remember this formula. After making the cut, we should use the formula 3c minus r dash, where c is the number of cuts to make the structure open tree like structure, and r dash is the number of restraints to make the joint rigid. Let's see how to use this formula for these two frame problems. Okay, so for this problem, suppose we are asked what is the degree of static indeterminacy for this case 1 and case 2. So let's see how we will use this formula here. So we will make a cut from here. So we have make only one cut. Only one cut is needed to make it an open tree like structure. We do not need any other cuts, right? Because from one cut only we will get these two structures, and both these structures qualify to be a open tree like structure. So one cut is sufficient. So we have made this cut. Now the formula says degree of static indeterminacy is 3c minus r dash. So ds will be, how many cuts we have made here? Number of cuts are one, only one cut we have made, minus number of restraints to make each joint rigid. So for this structure, every joint is already rigid. So this joint is rigid, right? It's a fixed support. It is a rigid air support, and this joint is also rigid. This joint is rigid, and this joint is also a fixed support. So it is also rigid. So we do not need any restraints, any other restraint to make this structure, make the joints of this structure rigid. So r dash is 0 in this case. So ds we will calculate will be 3 in this case. So degree of static indeterminacy will be 3 for this case. Now let's see case number 2. Here if we have to calculate the degree of static indeterminacy, we will make a cut here. Okay, so this cut will result in two structures, two open tree like structures. Okay, we will have a structure, one structure like this, and we will have another structure like this. So this structure is also open tree like structure because it has one root and no closed loop branches. It has one root and no closed loop branches, but the difference is does not have a rigid support here. It has a hinged support here. So here we have to do some extra things. Okay, so ds is equal to the formula we know, it is 3c minus r dash. Okay, ds will be how many number of cuts we require to make it an open tree like structure. We require just one cut. So 1 minus number of restraints, how many restraints we require it to make it a rigid, make the joints rigid. So here we do not need any restraint because it is already rigid. Here we also don't need any restraint because it is rigid. This joint is also rigid, but here it is a hinged joint. Okay, so here we need one other restraint to make it a fixed support. Okay, suppose it would be a roller support, then we would need two restraints, because here we just need to stop the rotation part. Okay, if we stop the rotation part of this particular hinge, it will become a rigid fixed support, right? Here we need to stop this horizontal movement as well as the rotation. Therefore here we require two restraints to make it a rigid support. I hope it is clear. For hinge joint, we require only one restraint, that is we need to restrain the rotation of the hinge in order to make it a rigid support. But in case of a roller support, we also need to restrain the horizontal movement and as well as the rotation to make it a rigid support. Therefore in this case we just need one restraint to make it a rigid support. Therefore r dash will be 1 in this case. So ds will be 3 minus 1 2. So here in this case the degree of static indeterminacy is 2. Let's see some more complicated things. So when we have hinge, okay, so when we have hinge, the formula will be same. Suppose this is the structure, we will cut this structure like this. So when we will cut this structure, we will have a structure like this and we will have a structure like this, let's say. So we will have a structure like this. So whenever we have a hinge, so let's see how the things are changing. So these two are open tree like structures, right? So we just need one cut here. So ds we will calculate using our formula 3c minus r dash. Okay, so ds will be number of cuts we require is 1, like only one cut we have made. Number of restraint, no restraint is required here because it is already a rigid support. No restraint is required here. Let's analyze this hinge at the last. No restraint is required here. Only one restraint is required here, one restraint against rotation, right? So one restraint here. So whenever there is a hinge, we require so restraints in case of hinge. So in case of hinge, the restraint required is number of members connecting that hinge minus 1. So here, how many members are connected to that hinge? Please, can you answer me in the comment? How many members are connected to this hinge? Two members, right? So two members, one member this and another this. So two members are connected to this hinge. So number of members connected to the hinge minus 1. So restraints in this case will be 1 for hinge. Okay, I hope it is clear. In case of a hinge, how we'll calculate the restraints? The restraints will be number of members connecting the hinge minus 1. So here we have one restraint required here, one restraint we require here. So total number of restraints are 2. So degree of static indeterminacy will be 1 in this case. Okay, I hope this is clear. So we'll just quickly solve the problem, which is the gate question here. Let's see how to solve it. So in this case, we require how many cuts? One cut here, one cut here, one cut here and one cut here. 4 cuts we require. So when we will see the structures, so it will be a one structure like this, another structure like this, right? So these are the three structures we have made. So all these three structure qualifies to be a open tree like structure. So I hope it is clear. So we require 4 cuts in order to make an open tree like structure. Okay, so 4 cuts we require. Now we know that we require 4 cuts. So degree of static indeterminacy will be 3c minus r dash. So number of cuts we require are 4. So 3 multiplied by 4 minus, let's see number of restraints now. It's a hinge support, so how many restraints we require? One. Hmm. It is a roller support, so how many restraints we require? Restraints against horizontal movement and restraint against rotation. So two. Here it is also a roller support, so how many restraints we require? Two. Okay. So, but and now we have hinges also. For this hinge, how many members are joining? Two members, one member this and another member this. So here 2 minus 1, 1 restraint will require. For this particular hinge also, two members, one member this and another member this. Two members are meeting at this hinge. So number of restraint will be number of members joining the hinge minus 1. So 1. So total how many restraints are there? 1, 2, 3, 4, 5, 6, 7. So 7 restraints. Okay, so degree of static indeterminacy will be 12 minus 7. So degree of static indeterminacy will be 5 in this case. So see how quickly we have calculated the degree of static indeterminacy for the rigid frame using the formula 3c minus r dash. I hope this is clear to you. You can again revisit this recording. I'll share the recording on YouTube maybe. And then in the next session, if you have any doubts, you can ask me. Okay, so it is already 5 p.m. now. So is it okay if I close the session for now? Or if you have any doubts, you can ask me. Is it okay? Okay, thank you so much. And bye for now and happy Diwali to you and your family. Thank you so much for listening.